All right, we're going to finish the titration problem that we were doing on Wednesday. All right. Is this where we were at the pH is equal to pKa at the half equivalence point? Is that where it was, or was it somewhere else? Does anybody have that? Is that where it was? Okay. All right, so the easiest question on the test is going to be calculate the pH at the half equivalence point, because then all you have to do is take the pKa. And so, of course, to take the pKa, the Ka will be given, and you just take the negative log of the Ka, and that is equal to your pKa, and that is equal to the pH at the half equivalence point. All right, so when you have a titration, there are some that are very easy. Well, this one is the one that is very easy. Calculate the pH at the half equivalence point. There's no calculation to do because you probably already have your pKa written down. Your pH is equal to your pKa. All right, so that is the pH at the half equivalence point. Then we went through the calculation. Every calculation for pH at the half equivalence point will work out exactly the same. So you do not have to work it out again. The pH is going to equal the pKa. All right, so we have calculate the pH, initial after 20 mils, equivalence point, half equivalence point, after 70 mils of HCl is added. All right, so now we're going to add 70 mils of the HCl. All right, so the HCl, if we look back, we see that the HCl is a 0.2 molar, and our NH3 is a 0.2. So we have a 0.12 molar for the HCl and a 0.2 molar for the NH3. All right, and the NH3, that's what was in our flask, and every time is 35 mils. The HCl is in our burette, and we are adding the HCl. All right, and so our H plus, which is our HCl, it said 0.12 molar. So we're doing MV is equal to MV. It said we're going to add 70 mils of that. And now we want the molarity, now that the volume is 105. I got that because the NH3 is the 0.2 molar. And we're doing, again, MV is equal to MV over here as well. And we had started with 35 mils in our Erlenmeyer flask. And we want the concentration now that the 70 plus 35 mils is 105 mils. All right, so when you get a titration problem, you're going to do MV is equal to MV a lot of times. All right, so our equation, or the reaction that's going on, is the one that has H plus in it and the one that has NH3 in it. And there is only one of those, and that is your Ka reaction. So it is your NH4 plus in equilibrium with H plus and NH3. So make sure you know your three reactions. You can write them reverse if you want. I will always write them in the Ka, the Kb, or the Kw reaction. All right, and so this is my Ka reaction. All right, so we push the buttons and we get our concentrations and we put them into our initial. concentration. So the NH4, we didn't add any NH4. We added 0.12 molar HCl, 70 mils. We had in our flask 0.2 molar of the NH3, 35 mils of that. And so when we push the buttons, we get our concentration of NH3 is a, now we'll just go, it's a repeating decimal again. All right, so the 0.2 times the 35 divided by the 105, that is a 0.06 repeating. All right, and so it should be 2 sig figs. I usually round at the end. All right, and then my H plus concentration, 0.12 times 70 divided by 105 is a perfect 0.08. All right, so that is our concentrations. Now, with all of these, something on the right has to be 0. So when both of your numbers on the right are not 0, you have to do a new initial. So your new initial, one or both, if it's equilibrium, then both of them go to 0. All right, so the smaller one you see is the NH3. So it is going to 0. The smaller one goes to 0. So minus 0.066 molar minus 0.066 repeating molar and plus 0.066 repeating molar. All right, and so we subtract 0.0 repeating the 6 molar, and we get a 0.013 repeating. All right, and here we have our 0.066 molar. All right, so when you have a reactant and a product that are not 0, all right, well, first things first, this is not a buffer because your H plus is not 0. So if your H plus is not 0, one of the two things on the right, if one of those things is not H plus, you can never have a buffer. So this is not a buffer. Our weak base is a concentration of 0. To have a buffer, you have to have concentrations of your NH4 plus and your NH3 in your new initial. NH3 is 0. All right, we also know if we have a reactant with some concentration and product with some concentration, when you go back to the equilibrium, minus X plus X and plus X, you are going to neglect this X and you don't have to check it. We do not have to check it. The only reason why we would solve this is if the question was, what is your concentration of NH3? That is not the question. The question is, what is the pH? Well, since we already have our H plus concentration, then the pH is equal to the negative log of your H plus concentration. So that is equal to the negative log of 0.013 repeating. And so you take the negative log of that answer, and you get 1.88. And so your pH is equal to 1.88. All right, so we went past the equilibrium, the equivalence point. So when you go past the equivalence point, you're going to have excess H plus if that's what you're titrating with, or you're going to have excess OH minus if that's what you're titrating with. And so you will either, in this case, we had our concentration of H plus. If we did a strong base with a weak acid, past the equivalence point, you would have excess OH minus, and then you would go right to the POH. All right, so then it says to graph your points. And so we're just going to sketch a graph. We had all of our points together. All right, so we'll make it very generic. All right, so here's your pH, and here's your volume of HCl. So we know when we're adding the volume of HCl, the pH is going to go down. So you start at a high pH because we had 0.2 molar NH3 in there, and then the pH is going to go down, and then it's going to go down sharply, and then it's going to level off. All right, and so here is your equilibrium point. And when we calculated the equilibrium, it was a volume of 58, I think. Pretty sure it was a 58. 58. So this is 58. All right, and when we were at the equivalence point, this was a 5.19. All right, so you don't have to draw it to scale, but you would have to label it. And so then here is your 29 mils. All right, you'll say we didn't do a 29 mils. Well, that's the half equivalence point. If the equivalence point is 58 mils, then half of that is 29 mils. And so we go to our half equivalence point, and that pH was a 9.25. So we go up here, come over here, and we say this is the 9.25. All right, and then you can label your other points. We added 20. After 20 mils, it was 11.28. All right, so then here somewhere we have our 20 mils, and this is your 11.28. No, that wasn't. It was 9.53. Sorry, 9.53. The 11.28 was the initial. So before we added anything, it was up here at 11.28. And so at the 0 mark, when we were at 0, then it was 11.28. And then beyond it, by a few mils here, mark it at 70 mils. So we went past it a few mils. And then we had our pH here of 1.88. So again, it doesn't have to be drawn to scale, but you should mark your points and mark what those are. You're not going to be given graph paper, so it doesn't have to be drawn to scale. So sketch it, put in a few of your points, and that is what you're looking for when you have to sketch your pH curve. pH is always on the y-axis. If you're adding volume of HCl, then that's what it's going to go, and the pH is going to be going down. If you have volume of NaOH, then the pH is going to be going up. So those are the two choices for your pH. There could be some graphs that are given, and they'll say, what is the pKa of this acid? Well, you have to know that this big change in pH here, that's your equivalence point. And so all you got to do is go here and then go halfway from there to here, go up and read the scale, and that's your pH, because remember that the pH is equal to the pKa at the half equivalence point. And so you can get the equivalence point. That's the big change in your pH. So you have that volume. It's right there. It just goes straight down that incline. That's your volume at the equivalence point. Half of that, go up, read the scale. That is your pKa. Let's do a few more problems. So the titration one, that will be the longest, hardest question, although within that question, there are some easy questions. All right, let's look at aspirin. So aspirin is acetoacylic acid, and so you don't need to know the organic structure of aspirin. All you need to know is that it is a monoprotic acid. And you don't have to ask, is it strong or weak? Because you know aspirin is not one of the 6 memorized strong acids, so you know it's a weak acid. So you would write HA, like I write for all of my weak monoprotic acids. All right, the Ka for your aspirin is given. So your Ka is 3.0 times 10 to the minus 4. All right, so calculate the pH and percent ionization of 0.2 molar of your aspirin solution, HA. All right, again, there's 3 reactions, and when you're given HA and nothing else, there's a 100% chance that you're writing the Ka reaction. All right, and so initial, all you have is HA, 0.20 molar. 0 H plus, 0 A minus. None of that was in the problem. It simply said you have 0.2 molar. What is the pH and percent ionization? All right, and so you can't have zeros, so minus x plus x plus x, and so you have 0.20 minus x, x, and x. So remember, we have our shortcut Ca over Ka. If that is greater than 1,000, then we don't have to check our x value. So when you take your 0.2 and divide by your 3 times 10 to the negative 4, you get 666, and that is repeating. All right, and so you get 660, well, we'll round it 7. That is not greater than 1,000. So you cannot just neglect the x, and that's your answer. So you have your choice. You can do the quadratic, or you can do successive approximations. All right, so I always choose successive approximations. So x squared over 0.20 minus x is equal to 3.0 times 10 to the minus 4. So I neglect my x, and I'll get my x1 value. So 3 times 10 to the 4th, negative 4, times 0.2, and then the square root of that, and you get 0.0077. So that's as large as the number can be. So I plug that in. So this time that's going in right here, plug it in, and get x2. So I have 0.2 minus that answer times 3 times 10 to the negative 4, and then the square root of that, and that is a 0.0076. All right, that's as large as it can be. That's as high as it can be. We plug it in again, get x3. So 0.2 minus that answer times 3 times 10 to the minus 4. And then the square root of that. And you get 0.0076. All right, so that is your final answer for the successive approximations. And note that the difference is very minor. So if this is a multiple choice, it would be the same answer. If it is not multiple choice, well, then you have to show all your work. If you're not showing that the Ca over the Ka is not greater than 1,000 and you're just going with the first answer, you will lose significant points. Make sure you always check that and know if you have to do the quadratic or not, or the successive approximations, either choice. All right, so then to get the pH of that, you take the negative log of that. So negative log of 0.0076 is 2.12. All right, so again, if I'm not going to have a multiple choice where the answer is 2.12 or 2.11, which would be what you got if you took the first answer. But if this is show your work, you always have to do the Ca over the Ka. If it is not greater than 1,000, then you have to do the quadratic or successive approximation. All right, and so now we're going to do our percent ionization. So there's our pH, percent ionization. That is your X over the initial concentration times 100. If it asks for degree, then you just don't multiply it by 100. But if it's percent, you multiply it by 100. So your X value, 0.0076 divided by 0.20 times 100. So 0.0076 divided by 0.2 times 100 is 3.8%. All right, so that is how you get those. Now, let's see what happens when you swallow the aspirin. All right, so there's buffers in the stomach that buffer the pH in your stomach to 1. All right, so now we're going to have the pH of your stomach is 1. All right, now we swallow the aspirin, 0.20 molar of your aspirin. And now the question is calculate the pH and percent ionization. All right, so the same reaction, HA goes to H plus and A minus. All right, so now initial, we're in the stomach. Well, we had 0.20 molar of our HA, but now we know that the pH is 1. And so now we can see that the concentration of H plus, so if your pH is equal to the negative log of H plus, and so your pH is 1 is equal to the negative log of H plus, then you take the negative on both sides and then your anti-log, and you get a 0.10 is equal to your concentration of H plus. And so this is 0.10, and this is 0. All right, so here, again, we have something 0 on the right where there's no new initial. The only time you do a new initial is when you have non-zero concentrations on the right. Something on the right has to be 0. Something is 0. And so it cannot be 0, and so we're going to do the change. Minus x plus x plus x. In this case, we do not have to check the Ca over the Ka because you have an initial concentration of both a reactant and a product. And so you can always eliminate the plus or minus x, and you do not have to check it. If you forget that, it's just going to take you a lot longer, but it will not change anything. All right, so 0.20 minus x, 0.10 plus x, and x. And so now we have 0.10 plus x times x divided by 0.20 minus x, and that is equal to your Ka of 3.0 times 10 to the minus 4. All right, so again, anytime you have a plus and a minus x, that means you had a reactant and a product. You never have to check those. So you neglect. If you forget, you can check it. You'll get the same thing twice. Fine. It's just extra work that you don't need to do. All right. And so you get x is equal to 6.0 times 10 to the minus 4. And so when you add your 0.10 plus 6.0 times 10 to the minus 4, it doesn't change it at all. All right, and so the initial and the equilibrium concentrations are always going to be the same when you're starting with the two, one reactant, one product. Anytime you start with the one reactant, one product, the initial concentration is exactly the same as the equilibrium concentration. All right, but if you wanted the A minus concentration, it's 6.0 times 10 to the minus 6. If you want to know the percent ionization, you have to know the X value. All right. And so the pH is unchanged. The pH is still 1. That is not changing the pH when you add 0.2 molar to a 0.1 molar H plus. It is not going to change the pH. But your percent ionization is always X divided by your initial concentration of your HA times 100. So now we have 6.0 times 10 to the minus 4 divided by the 0.20 times 100. So that is a 0.30%. All right, so we started with a 3.8%. Again, Le Chatelier's principle, when you add a product, you shift your equilibrium to the left. Well, what does that mean? Well, you can't shift it to the left because this is a 0. What it means is much less is going to come to the right. All right, and so this is a much lower ionization for this HA, a 0.3% versus a 3.8%. So anytime you add a product, your percent ionization will always go down. The Shotley's principle, if you add a product, the equilibrium will shift to the left, which means that you're going to have less things on the right. All right. All right, let's do oxalic acid. So we used oxalic acid in lab on Thursday. All right, so oxalic acid. That is a diprotic acid. It is not one of the 6 memorized strong acids, so I will always write H2A for my weak diprotic acid. All right, so the question is to calculate the concentrations of everything in a 0.1 molar oxalic acid solution. All right, so initial, I have a 0.10 molar. Now it's a diprotic acid, which means that you're going to have 2 Ka values. You have 2 different reactions. So Ka1 is given 6.5 times 10 to the minus 2. We do not like that Ka value. Ka2 is much better at 6.1 times 10 to the minus 5. The chances of requiring successive approximation when your Ka is times 10 to the minus 2 is very close to 100% of the time. All right, so you have 2 reactions. So first one we always do is going to be Ka1. Always do that one first, and then you go to Ka2. That gives you your H plus and your HA minus. All right, and so the question was, what are all the concentrations in a 0.1 molar oxalic acid? Including the pH, we want all of the things. We want percent ionization, what is going on with our 0.1 molar oxalic acid. All right, so initial change, you have zeros. So minus X plus X plus X, and then at equilibrium. So 0.10 minus X, X, and X. So you have to take your Ca over your Ka1. We're doing the first reaction. And so when you take your 0.10, you have to see if this is greater than 1,000. It will not be. Divided by 6.5 times 10 to the minus 2. So when you take your 0.1 divided by 6.5 times 10 to the minus 2, that gives you 1.5. All right, nowhere close to 1,000. So you must do successive approximations or your quadratic, and this will change it significantly. All right, so the last one was pretty close to 1,000, and so it only took, the second one was basically its answer. All right, but when you are at 1.5, you know that it's going to take a lot more than just a single approximation to get the answer. All right, so you have x squared over 0.10 minus x is equal to 6.5 times 10 to the minus 2. So in this case, it might be when you get a 1.5 as your Ca over your Ka1, you may want to go with the quadratic. I'm going to go with successive approximations. All right, so I neglect my x. All right, multiply both sides by 0.1. I got 6.5 times 10 to the minus 2 times 0.1. And then square root of that. I got a 0.081. So x1, 0.081. I plug that in. So I have my 0.1 minus that answer times 6.5 times 10 to the negative 2. I get that answer, then I take the square root of that. So as high as it can be is 0.081. As low as it can be is 0.035. So we see that those are big differences. All right, so we got to plug that in. So 0.1 minus that. times the 6.5 times 10 minus 2, and then square root of that, 0.065. All right, so it goes back up. Now x4 is going to come back down. Plug that in, 0.065. Times the Ka and the square root. We get a 0.048. All right, so you see high, low. It's going to eventually get the same, 0.1 minus that. Times Ka, square root of that, 0.058. Plug that in, 0.1 minus that. X6, 0.052. Plug that in. .056. Plug that in. .054. Plug that in. .055. Plug that in. .054. And so now we have the same number that we got 2 times, and that is then our answer. We have a 0.054. We had 0.054. So 0.054 is our answer for X. All right, so now we know that, so I have my value for H plus 0.054. My HA minus 0.054. And then my H2A is 0.046. Well, you always want to give 2 sig figs for your concentrations. All right, so now that's Ka1. Ka2 is not going to be near the problem as Ka1 because Ka2 is 6.1 times 10 to the minus 5. All right, and when we write that reaction, we will see something else that even makes it easier than that. All right, so now our Ka2 is our HA minus going to H plus and A minus 2. And our Ka2 is 6.1 times 10 to the minus 5. All right, so now we have our HA minus from Ka1 is 0.054 molar. H plus, also from above, 0.054 molar. And the A minus 2 is 0. Again, change can't have a 0. Minus X plus X plus X at equilibrium. You have a 0.054 minus X. You have a 0.054 plus X, and you have X. So again, you have an initial concentration of a reactant and a product. You never have to check your X value, regardless of the Ka value. All right, and so you do not have to do it. If you do, fine. It's not going to change it. It's just extra work. And so when you have your 0.054 plus X times X, and your 0.054 minus X, and that's equal to your Ka2, which is 6.1 times 10 to the minus 5. All right, again, you're going to neglect any plus or minus x because all Ka values are small. All right, and so when you neglect your x's, you see that you have the same numerator and denominator. The 0.054s cancel. And so your x is 6.1 times 10 to the minus 5. All right, if you plug that in, you will not get a change, but you can check it if you want to. You do not need to. Anytime you have an initial concentration of both a reactant and a product, you never need to check that answer. All right, and so what we have is 6.1 times 10 to the minus 5 molar for our A minus 2. So that is your concentration of A minus 2. All right, so now we have all of our concentrations. All right, so when you take and subtract your 6.1 times 10 to the minus 5, 3 decimals minus 6 decimals, 3 decimals, it doesn't change it. When you add it, it doesn't change it. All right, and so again, when you have an initial concentration of a reactant and a product, that is also your equilibrium concentration. It does not change. When you have an initial of a reactant and a product, it will not change. That will be the same as your equilibrium. All right, and so if we want the pH of this, so we have all of our concentrations. pH is the negative log of your H plus, which was the X value of 0.054. So the pH value is the negative log of 0.054. And that is a pH of 1.27. pH of 1.27. All right, and you want the percent ionization of your H2A. And this is going to be quite a large percent ionization because your value of Ka is so large, comparatively speaking. All right, so you have your 0.054x divided by the initial 0.1 times 100. And you see that is a 54% ionization. That is a huge percent ionization. So as far as weak acids go, that is a pretty strong weak acid. All right, having a pKa or having a Ka value of 10 to the minus 2 is a very large Ka value. Also, if it says give all of the concentrations, of course, if you have water, anytime you have H plus, you have OH minus. So if you have a pH of 1.27, you also have a pOH of 12.73. All right, and so that gives you an OH minus concentration when you take the negative of both sides and take the inverse log. You get a 1.9 times 10 to the minus 13. So if it asks for the concentration of everything, all things, anytime it says give the concentration of everything, if you're giving the H plus concentration, you must also give the OH minus concentration because all of these are molarity, all of these are in water, all of these have both an H plus and an OH minus concentration. So you can do it by the pOH, or of course you can do it by the Kw. And the Kw is a constant, 1 times 10 to the minus 14. And that is your concentration of H plus times your concentration of OH minus. If you take the negative log of both sides of this equation, if I want to take the negative log of this side, the negative log of this side, then you get 14, when the negative log of 1 times 10 to the minus 14 is equal to the pH, and if you know your log rules, plus the pOH. So this equation and the pH plus the pOH is equal to 14, those are mathematically the same thing. So mathematically, These are exactly the same equations. So it doesn't matter if you solve for the pH or the POH by getting the OH minus concentration and taking negative log of that, or if you take your pH, 14 minus your pH. Again, that is mathematically the same. All right, let's try one where we work it a little bit different. So again, the unknown doesn't have to be the same every time. Let's say we are given a concentration of HF of 0.10 molar. And we know that it has a pH of 2.09. All right, so then you calculate the Ka. So most of the time you'll get a concentration and a Ka and you have to calculate the pH. But if you have the concentration and the pH, you can then calculate the Ka. So make sure you can do the problem either way. So again, you have three reactions, and this is the HA because HF is not a strong acid. Make sure you know the 6 strong acids. All right, if this was a strong acid, the pH would be 1. The pH is 2.09. 0.1 molar, negative log of 0.1 is 1. So in this case, I would sometimes use the HF because it's the same amount of work to write an A or an F. So again, generic works every single time. But if you want to write HF is an equilibrium with H plus and F minus, great. All right, so we're finding the Ka. That's what we need to know. What we do know is the initial concentration is 0.10. We also know that the pH, and so to be more specific about the pH is not equal to the negative log of any concentration of H plus. It is always the H plus at equilibrium. All right. Now note, if I had a concentration of H plus and I have a concentration of HA, my equilibrium and my initial would be the same. All right, but that's it. We had our concentration of HF of 0.1. The pH is 2.09. Nothing else was added. It doesn't say anything else was added to this problem. It didn't add HCl. It didn't throw it in the stomach where the pH was 1. That's it. I have 0.1 molar HF, 0.1 mole per liter. Stick in your pH probe. It says 2.09. All right, so it has to go to the right. So at equilibrium, you have 0.10 minus x, you have x, and you have x. So your Ka is x squared divided by 0.10 minus x. All right, so many times we're given the Ka and we're solving for x and we're finding the pH. This time they gave us the pH, and so this time we know that since the H plus is x at equilibrium, all we have to do is to be able to solve for our H plus concentration. So you plug in your 2.09 is equal to the negative log of your H plus concentration. And then you take the negative of both sides, your inverse log, negative both sides, negative 2.09. Your anti-log is your 10 to the x button. All right, and so that is equal to your H plus concentration. And we also know that that is equal to x. So when you push the buttons on your calculator, you get x is equal to 0.0081. All right, so then you just plug it in. So your Ka is equal to 0.0081 squared over 0.10 minus 0.0081. And you have your answer. And that is a 7.1 times 10 to the minus 4. All right, so that is your Ka. So then it says, so that's part A. We'll call it part B here. All right, I have HF. This time I don't know what my concentration is, but I know I have HF, and I know that my pH is equal to 3. Now we got to calculate the initial concentration. So now we have an unknown initial concentration of H+. All right, so now you have to have 2 out of the 3. So you have to have a initial and a Ka, find the pH, initial and pH, find the Ka, the pH and the Ka, find the initial. All right, so you have to realize in part B, we still have HF. In part A, we have Ka. Ka is a constant. And so that is what the Ka value is. It is a constant. You have the same reaction. This time I'm writing it as H plus and F minus. Again, if you use HA and A minus, that's exactly the same thing. All right, so now initial. We have an unknown. Call it Y. Call it whatever letter you want. All right, 0, 0. So change has to go to the right. We have an initial concentration of HF. We know what the pH is. So minus X plus X plus X. And so at equilibrium, I have my initial concentration, Y, minus X, X, and X. And so we have X squared over the initial concentration minus X is equal to Ka. And so we know everything here except for Y. So you can only have one unknown, and that's all we have. Because X is our concentration of H+. We have our pH. And so to get the pH, convert that to H+, take the negative of both sides, and then you take your log of both sides, and you get 1.0 times 10 to the minus 3. All right, so you need to be able to easily go from pH to H+. All right, so that's equal to my X. And my Ka, we solved it in the previous question. And so we just plug in all our numbers. 1.0 times 10 to the minus 3 squared over the initial concentration, which is what we're solving for. 1.0 times 10 to the minus 3 is equal to 7.1 times 10 to the minus 4. All right, so now we have to use our math to be able to solve for Y. We do not know if our initial concentration divided by our Ka is going to be greater than 1,000. So we can't make an assumption, so we have to say that it must matter. And if it doesn't matter, well, fine. But if it did matter, now we have the right answer. All right, so multiply both sides by Y minus 1.0 times 10 to the minus 3. All right, then you distribute your 7 there and there. And so you're squaring this. So you have 1.0 times 10 to the minus 6 is equal to 7.1 times 10 to the minus 4 y minus 7.1 times 10 to the minus 7. All right, so I distributed my 7.1 times 10 to the minus 4. All right, so then I have to then add 7.1 times 10 to the minus 7 to both sides. I need to add 7.1 times 10 to the minus 7 to both sides. And I get 1.71 times 10 to the minus 6. And that's equal to 7.1 times 10 to the minus 4y. All right, so now I have my y by itself on the right equal to a number. And then I have to get y all by itself. In order to get y all by itself, divide by 7.1 times 10 to the minus 4. Divide both sides by 7.1 times 10 to the minus 4. And that will give you the initial concentration. And that is a 0.0024 molar. So that is equal to my HF concentration. So the initial concentration here is 0.0024 molar. All right, and if you took that divided by your Ka, that is definitely a number. Well, I'll tell you what that number is. Divide that by your 7.1 times 10 to the minus 4. And that is equal to 3.39. So if you did not stick that number in here, you would have gotten completely the wrong answer. So when you can't tell if your Ca over your Ka is going to be greater than 1,000, you always assume it is not. You plug the number in that you have for X. So a common error is trying to make it easier and say, well, I can neglect this X. You do not know that you can neglect this X. You have no idea if your initial concentration, because we don't know what it is, divided by the Ka is going to be greater than 1,000. So you plug the number in. You have X. It's 1.0 times 10 to the minus 3. It has to go in everywhere where you have an X. There are some cases where it's not going to change it. In this case, it would have changed it tremendously. All right, let's try this one. Calculate the pH of a 1 molar NH4Cl. All right, so this one would be easy if you were given a Ka. All right, so no Ka is given. So there's no Ka for NH4 plus. All right, however, there is a Kb given. All right, so many people will quit as soon as they can't find the Ka for NH4 plus. No, I can't do this problem, and you say there's not enough information. Well, there is enough information. There is the Kb chart that has the NH3. So you must know that Ka times Kb is equal to Kw. So you don't need the Ka and the Kb. You need one or the other for this conjugate acid-base system. And so the Kb for NH3 is 1.8 times 10 to the minus 5. All right, and so to get the Ka, you take the Kw divided by the Kb. So the Ka is your Kw divided by your Kb. So 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. And that is a 5.6 times 10 to the minus 10. All right, and you love that number. That number, almost no matter what you pick for initial concentration, unless you have some ridiculously small initial concentration, it's going to be always way greater than 1,000. So if you take 1 divided by, 1 is our initial concentration, divided by the 5.6 times 10 to the minus 10, you get a gigantic number, some billion number, so way more than 1,000. All right, and so you don't have to worry about checking your X, because Ca over Ka is not just greater than 1,000, it is a heck of a lot greater than 1,000. It would never change it. All right, so now we have our NH4 plus, and so again, NH4 plus is simple enough to write. So you can write it as NH4 plus going to H plus and NH3. Or, of course, you could write it as HA going to H plus and A minus. That is the exact same reaction. All right, so initial 1.00, and it goes to the right. You can't have zeros. Minus x plus x plus x. And so you have 1 minus x, x, and x. So people get going too fast. X squared over 1 minus x. The most common error here is I found the KB and I plug in the KB. Wrong. This is the Ka reaction. Anytime you have H plus, anytime you write this reaction that has an H plus, this is the Ka reaction. When you're doing this equilibrium, make sure you're using your Ka constant. You always have a Ka and a Kb. Sometimes you're writing the Ka reaction. Then you use the Ka. If you're writing the Kb reaction, well, then you have to use the Kb. All right, so this is 5.6 times 10 to the minus 10. We neglect the x. We do not have to check this. And that gives us a 2.4 times 10 to the minus 5. All right, and so that's x, and we see that in our equation that x is H plus. That's another thing you always have to check is x or H plus, is x the OH minus, is x the either one. You have to know what your x value is. All right, and so it says calculate the pH, so we have to take the negative log of that. And we get a pH of 4.63. All right, so pH, you have ammonium chloride. That is your conjugate acid. NH3 is your conjugate base. So if you just have the acid in solution, the pH has to be less than 7. It is at 4.63. All right, so HF, back to HF, Ka is equal to, at this temperature, 6.5 times 10 to the minus 4. Remember, your Ka can change if you have a different temperature. But each problem is going to be at it. They should all be at 25, but they can be at different temperatures. You will never have to get a Ka at a different temperature. They're all at 25 off of your chart. But if the Ka doesn't match the chart, that just means that this problem was done at a different temperature. So when you're solving for Ka, you can't just look at the chart and say, there's my Ka, because it never changes, because the problem could be at a different temperature. All right, so when you're calculating Ka, you cannot just look on a Ka chart. All right, so the Ka of HF is 6.5 times 10 to the minus 4. I have a 0.10 molar NaF. Calculate the pH. All right, so here you have to recognize that Na is a spectator ion. I like to get rid of the Na. It would be Na plus, but it's gone. This is simply F minus. So I have a 0.1 molar F minus, and you have to know that here is your weak acid, and here is the conjugate base. These are conjugates, and this is the base. All right, so in this case, we have the base and only the base. We have 0.1 molar F minus. Didn't say any amount of HF. It just said here's the Ka of HF. And what's the pH of 0.1 molar F minus? Again, you look on the chart for KBs, there is no F minus listed. That's because in the Ka, they're not going to list them both. You're either going to have the Ka listed or the KB listed, and if you need the other one, your Ka times your Kb is equal to your Kw. You will have to calculate it, which is the case here. We want the Kb. We have the base. So the Kb is equal to the Kw divided by the Ka, which was given. So 1 times 10 to the minus 14 divided by 6.5 times 10 to the minus 4. And that is a 1.5 times 10 to the minus 11. All right, so there's our Kb. Again, 10 to the minus 11. You can solve if you want. You can take your Cb divided by your Kb, and you will see that this is tremendously greater than 1,000. You do not have to check for your answer to, you do not have to check your x value. All right, and so this is a weak base. Again, we have our 3 reactions. This one is the weak base. So F minus, or if you prefer A minus, plus H2O goes to HF and OH minus. So initial, 0.1. Water's a liquid, it doesn't matter, 0 and 0. All right, so both things on the right are 0. Reaction has to go to the right. So minus X, and at equilibrium, we have 0.10 minus X, X and X. So X squared over 0.10 minus X, which we will neglect and not need to check because our Cb over our Kb is tremendously greater than 1,000. And that is equal to 1.5 times 10 to the minus 11. And so your X value is 1.2 times 10 to the minus 6. All right, so again, you have to know what X is. In this case, X is OH minus. And so I will go to the POH. Negative log of that. 5.91. And so then the pH is equal to your 8.09. All right. You could have said, here's my H plus concentration. I know my H plus concentration times my OH minus concentration. That's my OH minus concentration, by the way. Is equal to 1 times 10 to the minus 14. All right, so you plug in your X, which is your OH minus. You can plug that in there and get your concentration of H plus. Take the negative log of that, and you'll get the exact same answer of a pH of 8.09. I always go with POH and pH, but again, same answer if you go with concentration of your H plus times the concentration of OH minus being your Kw value. All right, let's calculate the pH of 0.10 molar HF and 0.10 molar NaF. All right, so this one can be done a couple of ways. Again, now here it's interesting. So the Ka was given 6.5 times 10 to the negative 4. When you're given both HF and NaF, it doesn't matter what reaction you write. Actually, in this case, if you recognize this, you don't have to write a reaction at all. But if you don't recognize this as something that doesn't require a reaction, either one is fine. If I have a weak acid and a weak base, I always pick the acid reaction, but doesn't matter. All right, so my initial 0.1, 0.1, 0. So my F minus is 0.1, my HF is 0.1. Again, sodium is always a spectator ion, that is F minus. All right, and I have my Ka reaction. So the Ka value is 6.5 times 10 to the minus 4. I also know I have a reactant at some concentration. I have a product at some concentration. I do not have to check my X value. So minus X, X, and plus X, and plus X. So at equilibrium, I have 0.10 minus X, I have X, I have 0.10 plus X. All right, and so then I plug it into Ka. So X times 0.10 plus X over 0.10 minus X equals 6.5 times 10 to the minus 4. I have a plus, I have a minus X, I have a reactant initial, I have a product initial. Every time I have the initial concentration of both a reactant and a product, I know that the equilibrium concentration will be exactly the same. The X value will not change it. I will neglect my X values that are plus and minus, and I get X is equal to 6.5 times 10 to the minus 4. That is my concentration of H plus. And so the question was calculate the pH. pH is equal to the negative log of 6.5 times 10 to the negative 4, which is a 3.19. All right, so this problem can be done like that, and you will, it's really not that much longer than doing it a different way. All right, when I see this problem, I do not do it this way. I see this as I have HF, the weak acid, at some concentration. I have F minus, its conjugate base, at some concentration. And so now I know that I have a buffer. Once you recognize you have a buffer, and I recognize it up here, once you recognize you have a buffer, you do not have to write a reaction. Well, you have to write an equation. You have to write the Henderson-Hasselbalch equation, that your pH is equal to the pKa plus the log of A minus over HA. All right, so again, for a buffer, you have to have weak acid, some concentration, its conjugate base, some concentration, 0 H plus, 0 OH minus. That's all you got. Whether it's the initial or the new initial, you have a buffer. All right, so something on the right has to be 0, and there is something on the right that's 0. It is the H plus. But if you recognize that you have only the weak acid and weak base at some concentration, you have the Henderson-Hasselbalch equation. All right, and then your Ka was given, and so your pKa is 3.19. Negative log of that is 3.19. And so you would say that the pH is equal to 3.19 plus the log of 0.10 over 0.10. And so your pH is equal to 3.19. All right, so if you recognize it as a buffer, you do this. If you don't recognize it as a buffer, then you can go through the whole equilibrium. And again, your final answer is the exact same thing of 3.19. It's just a lot less work if you recognize it as a buffer, put it in the Henderson-Hasselbalch, and the answer just comes out. Again, it is the same math. It's just more work to do it the other way. It doesn't make any difference. If it says show your work, you're doing Henderson-Hasselbalch, great. Show work, you show it this way, that is great as well. If the question wasn't calculate the pH, but determine if this buffer is going to be acidic or basic, well, it just be just as simple to calculate the actual number. Remember, a buffer, the pH of a buffer is going to be very, very close to its pKa. So this would be an excellent buffer if you wanted something to be buffered at 3.19, which means you want it to have a consistent pH very close to 3.19. All right, let's try one more here. And this time, I'm going to have the same thing, except I'm going to have 0.10 molar HF, and I'm going to have 0.10 molar NaF, just like I had before, and I'm going to have 0.050 molar OH minus. All right, now this is one where you have to write a reaction. And you have to write a reaction that includes HF, F minus, and OH minus. And if I'm writing OH minus, I would probably just write F minus, because how do we get OH minus? Well, we stick in NaOH. How do we get F minus? We stick in NaF. All right, and so the only reaction that has the OH minus in it and the weak acid, weak base is the Kb. So you have to know to write the Kb reaction, where you have your F minus plus H2O goes to your HF and your OH minus. So your initial, F minus, 0.1. Water's a liquid. We never count it. HF, 0.10. OH minus, 0.050. So those are the concentrations. And you should notice right away that there is not a 0 on the right. Anytime you do not have at least 1 0 on the right, you go to a new initial. Something, if you're writing the three reactions, the Ka, the Kb, the Kw, something on the right or both things on the right have to be 0. If they're not, you have to do a new initial. All right, and so something on the right is going to go to 0, the one that is the smaller amount. And so we are going to run out of my OH minus here, 0, because we reacted 0.050, and that made 0.050. And so now we have 0.050 left of our HF, and we have 0.150 molar of the F minus. All right, and so now we recognize this as a buffer. If you do not recognize it as a buffer, then you will have to find the Kb, which is your Kw divided by your Ka, and then you can solve for X, get the POH, and convert it to pH. If you see that I have a buffer, and so you simply go to your pH is equal to the pKa plus the log of A minus over HA, and so that is your 3.19, and then you put in your A minus, which is your 0.150, and you put in your HA, which is 0.050. And you see that we are now at 3.67. So if you use the buffer system, the questions are much easier and faster to get to your answers. So I highly recommend practicing recognizing a buffer and using this equation. Again, you do it the other way, you will get exactly the same answer. It'll just take you another 10 or 15 minutes. All right, we will pick up there tomorrow. Test Thursday, yes.